Imagine looking at a suspension bridge. While we see the steel cables and concrete pillars, the actual stability of that massive structure comes from the specific angles of its internal supports. Angles are the invisible framework keeping our physical world standing. To understand how those forces work, we can start with something simple, a perfectly flat, everyday square. If we slice that square diagonally right down the middle, we are left with a right-angled triangle. We have three names for its pieces. The flat floor at the bottom is the base. The straight wall going straight up is the perpendicular. And that long ramp connecting them is called the hypotenuse. Down in the corner where the floor meets the ramp, we have a specific angle. Mathematicians use a Greek symbol for this corner, called theta. It functions like a placeholder for whatever the measurement of that tilt happens to be. Here is the core rule of this shape. If you open or close that hinge, changing the degrees of our theta angle, the lengths of the triangle's sides are forced to stretch or shrink in response. They are physically locked together. Trigonometry provides the mathematical framework for this predictable relationship between a triangle's tilt and its edges. Because these sides are locked, something helpful happens. If you keep a specific tilt, like 30 degrees, the relationship between the lengths of the sides stays the same. Whether you draw a triangle the size of a postage stamp or a massive pyramid, the ratio between its edges will match. This page of notes shows how we track these specific ratios using name tags. Sine compares the vertical wall to the long ramp. Cosine compares the flat floor, the base, to that ramp. And tangent compares the straight vertical wall to the flat floor. These concepts map directly to the physical shape. Sine involves these two outer edges. Cosine pairs the bottom and the diagonal. And tangent measures the vertical wall against the floor. These terms are practical tools. They let engineers and mathematicians quickly communicate exactly which two walls of a triangle they are measuring. We can place our triangle onto a map, a mathematical crosshair with horizontal and vertical axes. We rest its base on the horizontal line, pinning the corner in the center. If we swing that diagonal ramp like a compass arm, the tip traces a continuous path. The right triangle becomes the internal skeleton of the circle. This hand-drawn diagram shows how our crosshair divides the circle into 4 boxes, called quadrants. We start in the top right, the first quadrant, which holds every possible angle from 0 up to a straight vertical 90 degrees. When the arm swings past the vertical 90-degree mark, the triangle flips over into the second quadrant. As rotation continues, it flips into the bottom left third quadrant and finally the bottom right fourth quadrant, completing a full journey around the center. This spinning shape demonstrates that an angle pointing in any direction can always be broken down and understood as a simple right triangle. The dense conversion formulas found in textbooks are written instructions for tracking our spinning triangle. Notations like 90 plus theta or 180 plus theta act as geographic coordinates. They tell you exactly which new box on our map the triangle has flipped into. This section lays out the basic transformation rules. Depending on which specific boundary line you cross to enter a new box, your name tag might switch. Sine might become cosine, or it might stay the same. Our crosshair functions like a map where moving right or upward is positive and moving left or downward is negative. The plus or minus signs in these formulas simply track whether the triangle's sides are stretching into these positive or negative zones. Every part of this system works together as a logical tool to track how a single shape navigates space.